Hello AP students, we are going to enter the exciting world of oscillations and simple harmonic motion. Basically studying the behavior and math behind things that repeat their motion over and over again. For example, a pendulum swinging back and forth, as we are seeing here, or a mass on a spring that we pull down and then release. Periodic motion. Oh yeah. We'll essentially be looking at three different types of periodic motion situations. A spring with a linear spring constant, a simple pendulum, and a physical pendulum. The thing that's important to note about all of these is that one of the reasons it gets this term simple harmonic motion is because it's going to follow a sine or a cosine curve, where in position versus time, the object itself is oscillating back and forth between minimum and maximum amplitudes. So we're going to start with Hooke's law. Famous equation, F equals ma. Hooke's law is F is equal to negative kx. So this is a linear restoring force. The negative indicates that it's restoring. K is the spring constant, which is measured in newtons per meter, and then x. So we have a mass, and imagine you pull it some distance down and let go. It's going to oscillate back and forth between the equilibrium position. Now, this being AP Physics C, we get to do calculus. So we're going to take the acceleration equation and put it into dv dt. Take the second derivative of that. Why take the second derivative? Because we're looking to get a solution to this, ultimately to get to a period, solving for time, at the time it takes for one oscillation. We're going to get it to a second order differential equation so that everything is in terms of x with respect to t. This is a very tricky differential equation to solve, and really they don't expect you to be able to solve this. Instead, what we're going to do is hypothesize a solution. So first we get it into this form, divide both sides by m, and this is a generalized form that we're going to see several times as we're going through and doing these calculations and doing these derivations. So remember this form with the double derivative on one side and no derivative on the other side, and all the constants put together. So what could be a solution to this differential equation? Here's a possible solution. X is equal to the amplitude times the cosine omega t plus phi, which is the phase angle. Does this make sense? Well, we would expect a trig function to be a solution because it is this periodic motion repeating over and over again. How do we know that's the solution? Well, we're going to work backwards. We're going to take the derivative of both sides. So what do we get? We get dx dt is equal to minus omega a sine omega t plus phi. If we take yet another derivative, the second derivative, take the derivative of this again, we get minus omega squared a cosine omega t plus phi. You may be wondering, what is this phase angle? What does this mean anyway? The phase angle basically tells us where's the starting position. It's usually going to be somewhere between 0 and 2 pi. Every example I've seen in free response, it always seems to be 0. The only reason I put it in there is because it's on the Advanced Placement Physics Equations sheet. So basically just know that this tells you the starting position of the situation. Anyway, back to the task at hand. Is this a good solution to that differential equation? We take the first derivative, we get that. We take the second derivative, we get that. So now I'm going to take this and plug them back into this. So there's that differential equation, that pesky differential equation that's really tricky to solve. This, remember, is minus omega A cosine omega t plus phi minus k over m, and x is A cosine omega t plus phi. The A cosine omega t plus phi cancels out. They're gone. So, if omega squared is equal to k over m, it works. Let's look at the unit analysis. Omega, which in this case is called the angular frequency, we can also think of it as angular velocity. They're analogous. It's going to have units of radians per second. K is a Newton per meter. Mass is kilograms. Kilograms cancel out. Meters cancel out, and we're left with square root of 1 over seconds, which gives us 1 over seconds, so the units work out. Anyway, here's our result. We know that will work to that solution of A cosine omega t plus phi will work as a solution to the differential equation. Remember, the goal is to get the period. So remember, omega is equal to theta over t, angular displacement over time. What time are we talking about? The period, the time for one revolution. So that's 2 pi over t. So we can take this 2 pi and set it equal to square root k over m. So we have 2 pi t is equal to square root k over m. I solve this equation for t, and I get this lovely t is equal to 2 pi square root m over k. Does that gel with what we see on the formula sheet? The period of a spring is equal to 2 pi square root m over k. That's where this equation comes from. You could come to this through experimental means, doing an experiment with a spring going back and forth with a known spring constant, and you would discover that it would have that period. And we can get to it mathematically. So, in summary, for this part, here's our differential equation. So the general form of the differential equation for simple harmonic motion will be a double derivative on one side, the x on the other, and this stuff here, these constants. The solution to that is x equals a cos omega t plus phi. And the period is equal to 2 pi over omega, but here's where I want you to pay special attention. This stuff right here, this is omega squared. We saw that in an earlier result where it only works, this equation works if omega squared is equal to that stuff in there. So this is equal to omega squared, which means for all future situations, if you can get this equation, you'll know that this is your omega squared, and that there's this relationship between period and omega, where you can substitute this stuff in here for the omega to get your final equation for the period. A little tricky, I know. So let's do another example, and then I'll give you two to work on. So in general, you want to set up your differential equation, find the value of omega squared. It's those constants in front of the x, and then set period equal to 2 pi over omega, substituting in those values that you figured out. So let's look at a simple pendulum from the perspective of torque. Alright, so we have our pendulum, length L, gravity's pulling it down, torque is equal to I alpha, it's also equal to R cross F. I in this case is ml squared, R is L, F, it's a restoring force, so negative mg sine theta. Put this into our differential equation, where the alpha is equal to d squared theta over dt squared. How do we get this into the form that we're familiar with? Remember, we want to get the d squared theta over dt squared by itself. So we're going to put this over onto that side. So a few steps of algebra, you'll see that it's equal to this. D squared theta over dt squared is equal to minus g over L sine theta. Now here's where we're going to use a small angle approximation. For small angles, sine theta is equal to theta. Put it into your calculator, check it out, see that it's true. So only for small angles are we going to be able to move forward. What we're doing is, instead of having sine theta, we're just going to put theta. So there's our standard differential equation. Just instead of x, it's in terms of theta. Where's our stuff? The g over the L. That's equal to our omega squared. So t is equal to 2 pi L over g. This is the period of a pendulum. Period of a pendulum. There it is, 2 pi square root L over g. So I want you to go through this process that was laid out before you 2 times for 2 more situations. Here's a physical pendulum. Odd shape, rotating. Here's the axis of rotation is at P. The center of mass is somewhere down here, and the whole thing is rocking back and forth. Put the period in terms of R, M, G, and I, moment of inertia, and use torque. See if you can do it. You're following the same process that I set up the first 2 times. And here's the second situation, a torsion pendulum. So find the period in terms of I and K. This time torsion is equal to minus, this is a kappa theta, where kappa is the torsion constant. So this is the equation that you're using. So this is the equation that you're going to start off with. So in both cases you're using torque is equal to I alpha. In this one you use R cross theta. In this one you're going to set that equal to I alpha. Find your omega squared and solve for t. Good luck. Alright, so these 2 you're going to be finding, see if you can get these done for Monday. They're really quite straightforward. I would say there's maybe 4 lines that you'll end up going through before you get to the final period for both the physical pendulum and the torsion pendulum. Alright, I do want to go through an example. Mass is attached to a spring with a spring constant of 4.5 newtons per meter. The mass is resting on a frictionless surface that's pulled 12 centimeters from equilibrium and released. So here are the questions. What's the period? What's the maximum velocity? If the block was released at t equals 0, what is phi? What's the position, x, at t equals 5? And what is the velocity at t equals 5? So, real quick, period, pretty straightforward. We have the values, 3.24 seconds. V max, we're going to start with our solution, a cos omega t plus phi. Take the derivative, and we get that. And we know that the only time you are going to maximize v is when sine, or the biggest sine ever gets is 1 or minus 1. So basically v max is equal to minus omega a. I'm realizing that I have about 40 seconds left on this, so I'm basically not going to do much explaining, just go through and show you my solutions. So to find the phase constant, you go through this. The only possible solution that works is if it's 0. Position at time equals 5, we're starting with that. Plugging in our values, and with that, that's for finding the velocity at t equals 5. Well, it was nice seeing you. See you on Monday.